In our last video, we talked about how current and resistance are related, and today we're going to talk about how current is used to carry energy from one part of a circuit to another part. So, in general, a circuit is just a path that was designed to carry current from one spot to another. So a path that's designed to direct, provide, and or control the energy that goes through various components. So, sources of current, probably the most common source of current is either a battery or your outlet, power outlet. You can buy a little machine called a power supply that takes energy from the outlet and produces various volts. You could have a solar cell, which when the light shines on it, can produce a current. So a couple different sources. You could use this current in lots of different ways. Lighting is very common. Fans, just to cool things off, are nice. On the opposite side of things, sometimes you just want to create heat. A toaster, for instance, its sole purpose is to produce heat so that you can toast your bread. Sometimes you want to move something, so you could hook up a motor. Or your television screen or computer screen needs power. Your speakers or buzzers or beepers or things like that, they all need energy, and so you got to get energy to them. And then there are various ways of controlling how much current goes into a particular part. So resistors are very common to reduce the current that's used. Switches can turn current on or off. A diode can direct current. It's kind of like a valve. Current only goes one way through it. Capacitors can store charge, and so that if all of a sudden your supply of voltage dies off, capacitors can kind of kick in and keep that current flowing, at least for a while. Transistors can magnify current. Potentiometers are kind of like resistors in the sense that they reduce current, but you can control them. So you can control how much current goes through or how much voltage goes through. Also, you could have a transformer, and a transformer will take current that's at one voltage and either increase or decrease that voltage. And there's other sorts of controlling devices as well, such as inductors, which I think convert electricity into magnetic fields and back again. I'm not entirely sure what they do, but anyway, those are all different ways of controlling current in different parts of a circuit. So now, power is simply the amount of energy that gets used up per unit of time. We've talked about power before. It has a symbol of capital P. The units for that are in watts, and I think you remember that a watt is using 1 joule of energy per second. Power can come in all sorts of different sizes. Very simple devices might only use milliwatts of power. Other things might use watts, like a light bulb is kind of measured in watts, 60 watts or 100 watts. And certainly you could use kilowatts or even megawatts of power at times. Although I can't think of anything in my house that uses a megawatt of power, but still, they come in all sorts of different ranges. So, and in general, the power that gets delivered to any element in a circuit is equal to the amount of current that comes multiplied by the voltage. And so remember that current is coulombs per second, and voltage was joules per coulomb, and so the per coulomb and the coulombs cancel, and so I times V gives us joules per second, which is a watt. So that's our formula. So here's a couple specific examples. How much current is used when you light a room using 3 100-watt light bulbs? So to answer this question, the formula, the power that's required, is equal to current times voltage. And the power is 3 100-watt light bulbs, so that's 300 watts. The current is what we're looking for. That'll be our variable. And then voltage wasn't told to us, but I'm going to assume that that's kind of a standard out-of-the-outlet AC power, which would be 110 volts here in America. And so 110 here we can divide, and let's see, what does that give us? 300 over 110 is roughly 2.7 amps. So here's an interesting question. At 10 cents per kilowatt, how much does it cost to run a load of laundry? So I looked up, or I had to guess a number at first, and so I typed 10 amps. 10 amps is a little low for dryers. The quick search on Sears.com, the first 2 dryers I found there that were electric kind of operated with 30 amps. And they do not run on your typical 110 voltage. They run on about double that, so about 220 volts. So if we wanted to figure out how much does it cost, let's first figure out how much power a dryer uses. Power is current times voltage, and so that's 30 amps, 30 coulombs per second, times 220 joules per coulomb, and so that works out to 6,600 watts, or 6.6 kilowatts. And so if we wanted to figure out how much that costs, we might need to know how long we're running a dryer for. I'm just going to pick kind of a typical load of drying, might take about an hour. So if I run 6.6 kilowatts for 1 hour, that gives me 6.6 kilowatt hours, and at 10 cents per kilowatt hour, or $0.10 per kilowatt hour, the kilowatts cancel, the hours cancel, and so I got, as a quick calculation, it costs about 66 cents per load, which doesn't sound like that much, except when you start to think about how many loads of laundry you might do. We're a very small family, just my wife and I and our small daughter, and so we only run maybe 3 loads a week, but that's about $1.80 a week. And in 4 weeks in a month, that amounts to close to $10 per month. And like I said, we're a small family. You get to be a relatively large family, and you're running maybe a load of laundry a day, and that can be a pretty expensive part of your electric bill. So that's why, as old-fashioned as it may sound, putting your clothes out on the line during the summer might be a very good economical option. Plus, you're not heating your house by running the laundry and having then to cool it again using air conditioning and so forth. So here's another example. Suppose I've got 3 amps running across a 6 ohm resistor. How much power is used? That is, how hot would this resistor get? How much heat is being dissipated? So the formula we have for power is current times voltage. So I do know the current, but I don't know the voltage. So if we remember from before, the voltage through a resistor is equal to IR, and so that's 3 amps times 6 ohms. That's a voltage difference of 18 volts. And so we can go here and put in our 3 amps and 18 volts. That corresponds to about 54 watts, or about an average light bulb. That's going to get warm relatively quickly. Now, the last question I ask is, in general, how much power is dissipated when you move current through some wire with some sort of a resistance. And so instead of having, if we want an actual picture here, instead of having an actual number, I'll just call this I, and I'll call this R. So last time what we did was we calculated the voltage, and so voltage, remember, is IR. And so if I wanted to take my power equation, which is IV, and make a substitution and put this in its place, one more formula for power is that it could be current times current, which is current squared, times resistance. So that's kind of a fun formula. And another formula, instead of solving for, instead of taking this equation and substituting it for V, maybe we didn't know what the current was, but we did know what the voltage was. Then I could take this equation and rewrite it for V. I is the same thing as V divided by R. And so if I took IV and replace the I with V over R, I get another formula that is V, and then this V, that's a total of V squared divided by R. It's another formula for power. So, as a whole, we have three different equations for power. We've got I squared R. We've got the derived V squared over R. And we also have, just in general, I times V. So, thanks for watching, and be sure to tune back in next week as we talk about some more advanced circuits and how we can use some tricks and some principles to analyze even the most complex of circuits.